In this video, we're going to talk about an application of Raoult's law. So, if you recall from the previous video, Raoult's law talked about the relationship between the mole fraction of a solute, or a mole fraction of a solvent, rather, and its vapor pressure, how easily it was able to volatilize. Well, we can kind of infer from that if including a solute, creating a solution causes the vapor pressure to decrease, then it would naturally make sense that is going to cause the boiling point to increase. And if you look at a phase diagram for a solution, you can see here the slightly lighter colors correspond to what happens at for pure water. So here is the solid liquid equilibrium line for pure water. Here is the the liquid gas equilibrium line for water. Here's the triple point for pure water. And what we can see is that because of Raoult's law, because of the vapor pressure lowering, we can actually see that there is a gap, that the boiling point, the overall liquid phase, is significantly larger for the solution than it was for the pure water. But what's kind of interesting here is that we also can see that there is some kind of an impact on the freezing point of the water as well. This liquid region also has expanded into what used to be the solid region for the pure water. Now, the question that we would have to ask ourselves is, well, why is that? I mean, we can kind of rationalize the the liquid region expanding into the gas because of the reduction in the vapor pressure. But why this other change? Well, so we can see that the decrease in vapor pressure is going to increase boiling point. That makes sense. But what we're also seeing is that there is a freezing point depression. And the freezing point depression comes as a result of solutions are going to freeze at lower temperatures than their pure solvents because, again, the intermolecular forces that exist between the solute and the solvent are stronger than what existed between the pure solvent and itself. And as a result, that those stronger interactions are going to make it more likely that the liquid stays a liquid and that it freezes at a lower temperature because the freezing process is going to force those solvent molecules to have to kind of separate themselves and start to freeze kind of individually. Uh, so the whole point of today is to look at, can we actually calculate what these values are? So can I predict how much the boiling point is going to change, or how much the freezing point is going to change of a given substance when we turn it from a pure substance to the solution? And the answer there is yes. And not only is the answer yes, but we also see that the relationship is very, very similar. The boiling point elevation and the freezing point depression can both be calculated using similar kinds of equations. The boiling point elevation is represented by Kb, which is the boiling point elevation constant for the solvent, and every solvent has its own Kb value, and M, the molality. So how concentrated is the solution? How much solute is in there? And the freezing point depression constant equation is the same. Kf, the freezing point depression constant, which is solvent dependent, and every solvent has its own unique Kf value, and the molality. Now, what's missing from each of these equations is a discussion of one other important factor. And the important factor that we're missing here is something called the Van't Hoff coefficient. The Van't Hoff coefficient which is depicted by the term I, is estimating the total ionic concentration of the solution. And we can estimate I based on the number of particles a solute forms when it dissolves. So let's go here. So if we go to the whiteboard here and we look, we can see that the Van't Hoff coefficient, we can estimate this impact, this characterization, by the number of particles that are formed when the solute dissolves in the water or whatever the other solvent could be. Now for non-electrolytes, so if you think back to the examples we had with vapor pressure, when we were dissolving non-volatile particles, things like ethanol in water, sugar in water. For non-electrolytes, the Van't Hoff coefficient is simply 1, and so the equations that we have would not change whatsoever. But for things that are electrolytic, I is basically equal to the number of ions that we get per molecule. So for hydrochloric acid or hydrogen chloride, we would get an H plus ion and a Cl minus ion, 2 ions in total. I would equal 2 in that case. For sodium chloride, I would get sodium ion and chloride ion. That's 2 ions in total. My I in this case would be 2 also. For sodium sulfate, I would get 2 sodium ions and 1 sulfate ion. That's 3 ions in total. I would be equal to 3. For iron 3 chloride, I have iron 3 plus and 3 chloride minuses. It's 4 ions in total. I would be equal to 4. For calcium bromide, I have the calcium ion and 2 bromide ions. That's 3 ions in total. I is equal to 3. So what we can see is that from this standpoint, we can estimate based upon kind of looking at what would happen in our ionic equation. What would happen when this becomes an ionic equation? How many particles would it make? And that is multiplied into our equations for freezing point depression and boiling point elevation. So it's not just simply delta T is equal to KB times M. We can actually modify this. Let's change that. Is equal to I times KB times M, where I is the Van't Hoff coefficient, and our freezing point depression isn't this anymore. It's our change in freezing point is equal to I times Kf times molality. And once again, I is the Van't Hoff coefficient. Now, we'll see this Van't Hoff coefficient showing up in other occasions as well. And something I want you to also be aware of is that the Van't Hoff coefficient, using the methodology that we just talked about with net ionic equations, that's an estimate. In a lot of cases, especially when our I values are larger, what we'll find is that the actual value of I is going to be slightly less than the estimated value of I. And if you are given a value for I, then that's just what you run with. If you're told that I for calcium chloride is 2.87, then that's what you plug into the value for I here, not 3. Now, as I mentioned before, our Kb and Kf values do vary by substance, but you can see that every single substance has a unique set of values, and that those values do change based upon the nature of the material itself. So you can see that things that are nonpolar, like benzene here, have higher Kb, higher Kf values than things that are polar or have hydrogen bonding, like ethanol does. And so some of those differences that we can note do have a lot to do with polarity, do have a lot to do with size. There is a relationship between intermolecular forces in the substance and the Kf and Kb values that are associated with them. Now, the other thing that we need to strike on here is that our delta Tb means change in boiling point. So since this is a boiling point elevation, we will add delta Tb to the normal boiling point to find out what the new boiling point will actually be. And the same thing for the freezing point. Delta Tf means a change in the freezing point. But since this is a depression, we will subtract the freezing point depression from the normal freezing point to find out how far depressed the value actually is. So in the next video, we will go through and do a couple of examples of some of these kinds of calculations regarding freezing point depression and boiling point elevation. Until then, have a good day.